Hello everybody. So in this today's lesson I will discuss about the concept of carryover factor and what is your rotational stiffness for beam. To discuss this concept I have taken a question from GATE 2013. Okay. In this question, here in this figure, all members in a rigid jointed frame shown are prismatic and have the same flexural stiffness EI. Find the magnitude of bending moment at Q. Okay, you have to find the bending moment at Q. Okay, so let's start. The very first thing is, what is carryover moment? Okay, so carryover moment, do you know what is it? Well, if you don't know, for you, let's say this is a propped cantilever beam. Okay, and now you are applying a moment at this simply supported pinned end. Let's say this is M. Now how much moment is carried at this end? Okay, what is the moment at this end? Let's say this is mx. Let's say the value of this mx is your mx is equal to k times m. Okay, and here k is known as your carryover factor. Okay, now our task is we have to find this k. Well, to solve or to find this moment at fixed end, we will use our conjugate beam method. Okay, and what is conjugate beam method? By this method we can find your slope and deflection by the using of shear force and bending moment. How? Well, in this problem I will discuss that. So now to solve this problem, let's consider this beam. This is your beam, this is propped end, and this is the applied moment M. Now I can replicate this beam by using a simply supported beam. This is the simply support beam. Here is the applied moment, but as I have removed the fixed end or fixed support, I have to apply a moment here. This is mx. Our task is we have to find the mx. Okay, so now consider at step 1, the first step is apply the moment m at right side, and the second step is apply the redundant moment at the left. Okay, this is mx. So this problem now is equivalent to case 1 plus case 2. So in case 1 we will first find the slope here at support B. Let's say this is A, this is B. So here let's say slope is theta 1 and here slope is theta 2. Okay, and here also due to this redundant moment, the slope at left support is, let's say this is theta x and here this is theta y. While at support A the total slope is simply theta 2 plus theta x, and as this is a fixed support the slope is 0, so theta is 0. Okay, so next step is we have to find the value of theta 2 and theta x. Okay, so in this case 1, if this is the beam with applied moment m, what is the bending moment? The bending moment looks like this. This is m. Now convert this bending moment into your m by EI diagram. Okay, now apply a load like this on this beam. Because why the upward load? Because here the deflection due to this moment is upward. Okay, now at this point apply support, pinned support. Here is also pinned support. Okay, we are going to apply the conjugate beam method. So to find theta 2 or slope at A, we have to find the shear force at this point, or the shear force at support of this conjugate beam. Now solving, so what is the reaction here? So reaction RA is coming as your half times L, the span is L, times M by EI times L by 3 divided by L is equal to ML by 6 EI. This is the total area of load, and this is acting at a distance of L by 3 from B. Okay, now similarly for case 2, let's find theta x. So here the moment is mx, so the moment diagram becomes like this. This is your mx. Now convert this diagram into M by EI diagram, and here the deflection is downward, so we will apply downward load to the conjugate beam. To find theta x, we have to again find the reaction here. So here reaction or RA is coming as your 2 mx L by 6 EI. Just take moment about this point, you will get this value. Okay, and now theta 2 is known to you, also theta x is known to you, and you know that theta 2 plus theta x is 0. Okay, so we are getting mxl times 2 by 6 EI plus your ml divided by 6 EI is equal to 0, or mx is coming as m by 2. Okay, and here mx was k times m by 2, so k is coming as half. So half is the carryover factor here, and carryover moment mx is simply m by 2. As the sign is positive, so the assumption of our direction, that is the mx is acting in clockwise manner, is correct. So now you have got the concept of your carryover moment. The next part, or the second part of this problem, is we have to know what is the rotational stiffness for beam. By definition, the rotational stiffness of beam is the moment which is required for unit rotation at simply supported point. Okay, so consider any beam. Let's say this is a beam, it has a support here pinned, and this is also pinned. Now the rotational stiffness is calculated based on the moment required at this point. This is the pinned or simply supported point for unit rotation. If we apply moment, it will rotate. So to produce this unit rotation, how much moment is required? That is the rotational stiffness of your beam. Now let's find for different the far away condition. It may be pinned, it may be fixed like this. What is the rotational stiffness? For the very first condition, let's consider the far end is free, completely free. It can move upward and also it can rotate freely. Okay, so there is no restraint. So of course, to produce unit rotation like this, you need zero moment. So rotational stiffness for this type of support is 0. Okay, now let resist this vertical movement. So for that you have to provide a pinned support here. Now to produce this unit rotation, how much moment you need to apply? Okay, so let's say you have applied a moment. What is the moment diagram? The moment diagram is like this. This is M. Again, convert this beam into a conjugate beam. So provide pinned support here, and as the deflection is upward, you have to apply a load at upward direction with magnitude M by EI at this point. Okay, now to find the rotation at this point, you have to calculate the shear force which is acting at this support. Okay, so again if you take moment about point A, you will get the reaction at B, and the reaction is coming as ml by 3ei. Okay, so the rotation here is ml by 3ei. This is the rotation at this support or at this point. Now if I make theta is equal to 1, in that case the unit rotation will be produced, and for that the moment is coming as 3ei by L. Okay, so for this type of support condition, your rotational stiffness is 3ei by L. Okay, now let's say far end support is fixed. This is pinned support, and again you are applying a moment M. Okay, so how much moment is required to produce this unit rotation? Okay, again break this beam into two parts. First part is both the support are simply support, you are applying moment M, and second part is both the support are pinned, but due to this fixed support you are applying a redundant moment. Okay, let's say this is mx. Now you have already learned what is carryover moment. Here this is fixed support and this is the pinned support. Okay, so if you apply your moment m at pinned support, how much moment is carried by fixed end? This is simply m by 2. Okay, so here this mx is m by 2. Now we will separately calculate the rotation at support B. This is A, this is B, this is A, this is B. Okay, so for the left one, well, again apply the conjugate beam method. This is the moment by EI diagram. Okay, this is the support, and as the deflection is upward, you have to apply an upward load. Okay, and here to calculate the slope at B, you have to find reaction RB. Okay, here reaction RB is coming as your ml by 3ei. Okay, the second case, again this is B, this is A, this is the m by ei diagram. Here m by 2ei because moment is m by 2. Okay, and here the deflection is downward due to this type moment, so you have to apply a downward load in the conjugate beam. So to find the slope at B, you have to again find the reaction RB. In this case RB is coming as your ml by 12ei. Okay, so here the slope is anti-clockwise and here your slope is clockwise. So take this positive and this is negative. So total slope at this point or at B is coming as ml by 3ei minus ml by 12ei, which gives us 3 ml by 12ei. Okay, so again we have to make this theta here at this point. The total rotation is unit, so make theta is equal to 1. So how much moment is coming? This is coming as 12ei by 3l or 4ei by l. This is the rotational stiffness when your far end is fixed. Okay, so now you have got three values. First one is when this far end is 0, the rotational stiffness is 0. When this far end is pinned, the rotational stiffness is how much? 3ei by l. And when this far end is fixed, your rotational stiffness is 4ei by l. Okay, now go back to the point. So this is the problem. So here the rotational stiffness due to this TS part is 0 because there is no support, it is free. For this part this is fixed, so it is 4 EI by L, or L is given as 4 meter, so this is coming as EI. Now for TQ again this is 4 EI by L, but L is given as 2 meter, so this is coming as 2 EI. For this one this is pinned, so the rotational stiffness for TP part is 3 EI by L. Here L is how much? 3, so this is coming as 3 EI. So total rotational stiffness of this system is how much? 0 plus EI plus 2 EI plus EI, so 4 EI. Okay, so if you apply total moment of 4 EI, the share of this TQ is how much? Only 2 EI. So for total 4 EI moment, TQ have 2 EI share. And now in this problem, how much moment has been applied? 100 kilonewton moment has been applied. So for this 100 kilonewton moment, how much share do TQ have? 2 by 4 times 100. So TQ have your 50 kilonewton meter moment. Okay, so 50 kilonewton meter. Here is T, here is Q, and the question is how much moment, how much bending moment at Q? Well, simply here you are applying 50 kilonewton meter moment. Okay, so here M is equal to 50. How much moment is being carried at Q? Simply mx, which is m by 2. So here moment is 50 by 2, that is 25. So the answer for this question is 25 kilonewton meter.